Welcome back. Last time we were talking about sine and cosine functions primarily and what happens when we mess around with the argument a little bit. We already know from using the unit circle that cosine and sine x, cosine x and sine x, have period 2 pi. What does that mean? It means they repeat themselves every 2 pi. So this in black is cosine x. We're at 1 at 0. We expect to be back at 1 in 2 pi. You'll notice there's one distinct wave in this, or if you wanted to think about these as wave crests, you could call it two, but better to think of this as one wave right there. What about cosine 2 pi? Well, we know that for cosine 2 pi, cosine of 2 times 0 is still 0, so they start at the same place here. But cosine 2 pi goes to 0 at pi over 4 faster, because 2 times pi over 4 is pi over 2. Cosine pi over 2 is 0. I've put cosine 2 pi in blue, and what you can see is that where cosine x has one wave, visible wave, this has two. And I'm looking at the bottom here right now. You'll notice also that I just put this graph from 0 to 2 pi instead of making it symmetric, and that's simply because there's going to be a lot of drawing, and what I need to get across can be done in just one period of the usual function, which is 0 to 2 pi. In general, if you have cosine nx, if you put an n in front of the x, whatever the number is, the period is going to be 2 pi divided by n. And I would like you to think about why that might be the case for a while. So how is cosine nx compared to cosine x, the graph of that? And let's think about it. When x is 0, cosine n times x, n times 0 is 0, so it's still cosine 0, which is 1, which I bet everybody knows now. So we're starting in the same place. Where is the first place that cosine x goes to 0 in this stretch from 0 to 2 pi? Well, it's at pi over 2. When is this equivalent to pi over 2? When is nx equal to pi over 2? Well, it's going to be when, so we're going to divide the n out, and it's when x is equal to 2 pi, pi over 2n. Basically, we're dividing out the n. And so when x is equal to pi over 2n, cosine n times pi over 2n will be, the n's will cancel out, and you're going to have cosine of pi over 2. And this is the first place it hits 0, which will be right here. When we were in cosine 2 pi, n is 2, so we figured out what is pi over 2 divided by 2. It's pi over 4, and sure enough, that's the first place that it hits 0. I would like you to have some kind of feeling for why we're squishing these together. We're getting more waves every positive number that we put up. So in general, for cosine nx, it has a period of 2 pi over n. This is going to be really important when you get into physics and doing things like harmonic analysis or acoustics. These things show up everywhere. So you'll definitely want to be familiar and comfortable with the basic graphs and what changing them around a little bit does. From algebra, you already know that, suppose we do this. So right now, here is y is equal to cosine x. What would the graph look like y equals 2 cosine x? Well, we multiplied a function by a positive number greater than 0. Basically, when x is 0, this is going to get up to 2. When x is pi over 2, it's still going to be 0. When x is pi, it's going to be cosine of pi is minus 1, but 2 times minus 1, and let me get a little stretch down here, it'll be minus 2. I'm not going to spend too much time on this. Hopefully from your algebra you'll remember that this is just going to stretch this out, and it's going to do this to it. If you put a negative in front of that, it would flip it around the y-axis. So I hope that everybody kind of remembers how functions are changed and manipulated by multiplying them by numbers or putting a minus sign in front, things like that. Let's take a look at the sine function. I think we already have shown that sine of x and cosine x are really related. They're very similar. They're just offset by pi over 2 degrees. But let's take a look at sine x. Let's open this here. Once again, I'm putting in convenient places that I know where these function values are. Okay, so we're going to graph y equals sine of x. So when x is 0, I know that sine x is 0, so this one starts right here. I'll put in my 1 and my negative 1. When x is pi over 2, sine of pi over 2 is 1. Sine of pi is 0. Sine of 3 pi over 2 is negative 1. And sine of 2 pi is 0. And this is what this looks like. Once again, this has period 2 pi. And specifically what that means is if you pick any recognizable point on here, it's going to come back to that exact point in 2 pi. So we take this point right here, we look that it's the same point right here. And what do I mean by the same point exactly? Isn't it 0 here? Doesn't it have period 2 pi? This is 0, but look where it is. On this, it's taking this entire run right here. It won't be until we pass 2 pi that it starts going up again here. Even though it hits 0 here, the function value itself is going down. So when we're saying that it has period 2 pi, what I'm saying is if you cut this piece out and just stuck it every 2 pi this way or this way, the function would look exactly the same. It just keeps going and going. Similarly, if you end up making sine of 2x, the same thing's going to happen. And I think I'll do this one more time just so you can see this, and then you'll probably get this. And I could do sine 3x or 4x or 5x, but figuring out the exact place on the line isn't hard, but it would take more time than you're going to probably want to sit and watch me do. And the idea is the same. So what am I going to do? I know that all the places that I recognize immediately are going to happen twice as fast, so I'm going to cut these in half. Pi over 4, this is 3 pi over 4, this is 5 pi over 4, and this is 7 pi over 4. If I made sine 3x, I would have cut them in thirds. And the first couple I know offhand, but the rest I'd actually have to be careful of, which you should be when it's time to do it, if you need to. So when x is 0, once again, sine of 2 times 0 is 0. So these start in the same place. This time, when x is pi over 4, sine of 2 times pi over 4 is sine of pi over 2, that's 1. And similarly, we're going to go here, we're going to go here, 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 and here. And I've only got a little bit left on this one, so I just want to show you this. And once again, what we see is that it is essentially doubled its shape, or it got crunched in like an accordion, however you want to visualize it. And we'll be right back.